Welcome to the next installment of our acid-base chemistry unit with APIB chemistry at Allen High School. We are right in the midst of a titration, and we've discovered earlier at the very first step that we're halfway to the equivalence point. By the time we're done, you're going to see that this is a very, very easy type of a question. Now, we have added volume to volume. Don't forget, DSE will help you at every step of the way. So volume to volume means we had a dilution, and we've added 10 mLs of our base, and its original molarity was 0.200 molar. Now we started with 40 mLs of acid, and we just tossed in 10 mLs of base, so that's our new volume. And we get our new molarity of base, and it's 4 times 10 to the minus 2. Now, for our acid, we have to dilute as well, but we started with 40 milliliters of the acid times its initial molarity, same final volume, and we'd get our molarity of our acid in the same manner. And lo and behold, it's 8 times 10 to the minus 2. We're halfway to the equivalence point. We're neutralizing 50% of our acid. So we've got our start. We have no other source of that, and water we really don't care about. Now, this could come along if we added sodium acetate or something. We don't have any source of this other than what happens through our neutralization. Now, our hydroxide is still our limiting. So we're going to lose 4 times 10 to the minus 2 molar, and we gain that on the product side, no Q needed. So this goes to 0. This is 4 times 10 to the minus 2, and this is 4 times 10 to the minus 2 molar. Well, they should be the same because we've diluted 50%, neutralized 50% of this. Now, if we put this in, and I'm telling you, this is the long and winding road way to get at this. All right, but it works. So a DSE works every time. So if you don't know where to start, that's your starting point. So now I have 4 times 10 to the minus 2. Now remember, the results from a stoichiometry are typically going to hop into the initial of your rice. So that's 4 times 10 to the minus 2, and that's 0. Now, again, you want to use A for acid, B for base. There really is a reason for that. I promise you it will pay off if you use that symbol. All right, I'm kind of just walking through this because you should know how to do this by now. This is no different than what we did before. So now our Ka, we've already set up the expression, so I'm not going to do that again, but the number in front is greater than 10 times our K, so I can neglect that. This number in front is greater than 100 times our K, so I can neglect that. That just means the percent dissociation is teeny, tiny. Okay? So I'm going to end up with 4 times 10 to the minus 2 here times A over 4 times 10 to the minus 2. Those cancel, and all you have to do is state that. You didn't have to do any of that other work if you recognized it. As long as you stated you are halfway to your equivalence point, at that point, Ka is equal to your concentration of H+. Now, that means another way to write that is pKa, which is minus the log of Ka, is equal to your pH. Okay? It's actually a fairly simple calculation for this one. So in our case, pH and pKa, we have our Ka, we know Ka, so those are both equal to 1.3 times 10 to the minus 5th. So pH and pKa are both equal to 4.89. Now, what this means is if I didn't know my Ka, I could do a titration, measure my pH halfway to the equivalence point, and I could find an unknown pKa. which is what you're doing in your lab. Okay, so that one's not too bad, I hope. Now we're in the buffer zone. Halfway to the equivalence point is in the buffer zone as well. But we are in the buffer zone. At the end of this, I'm going to show you an equation that many people like. I'm going to stick right now to our framework. DSE. Doc saves everyone. If you'll do the framework, it might take you a little while, but it pays off in the long run. So we have to do our dilution. So for our base, we started with 15 milliliters. It was a 0.200 molar solution. We had 15 milliliters of our base, and we added it to 40 milliliters of acid. So we need a new molarity of our base. And the new molarity of our base turns out to be 0.0545. Okay? Now we're going to do the same thing for our acid. By the way, it's not unusual to write HA or HX as a generalized weak acid. So sometimes you can do that as a little bit of a shorthand. 40 times 0.1, we pretend we're starting fresh. Now this is 55 times the molarity of our acid. And if we solve for the molarity of our acid, we'd have 0.0727. All right, now acid plus a base, it doesn't matter weak or strong, it's a stoichiometry or a neutralization until one of them runs out. What's nice about these is there's no question what the limiting is. It's a 1-to-1 mole ratio. It's the smallest number, 0.545. Our base is still limiting. We're not at the equivalence point yet. That goes to 0. And this is 0.0182. There are some little short steps you can take, but you really need to show me sufficient work to prove your brilliance. All right? Now, remember, stoichiometries, the stop or the end of the stoichiometry is typically going to be your initial in your rice. So let's take a look at our rice. We would put our 0.0182. It's pretty much like adding a common ion. It's a variation on a theme or a different way to achieve a common ion. Now, I want you to notice something here. Have you noticed that in the buffer zone, we always have some of the acid and some of its conjugate? We could have some of a weak base and some of its conjugate. That's an important observation, right? Now, this is change. We don't know what it is, but it's an acid, so I'm going to use A. Okay, and now it's solved the same way. 0.0182 minus A, 0.0545 minus A and A. And just like we did before, use your little 100 times K test. Remember, AP is not going to require you to do the quadratic equation. AP and myself and chemistry in general, we care much more that you understand the concepts of what is going on in a titration than you know how to plug numbers into your graphing calculator to use the quadratic equation. So you're not going to have to use the quadratic equation on tests. Now, if we plugged this into K, K would therefore equal the 0.0545. Notice the lovely 1-to-1 stoichiometry. It really helps. 0.0182. And if we plugged in the information that we know for K, what we're going to find is that A is equal to 4.34 times 10 to the minus 6. So our pH, right, A represents our H+. So I like to use A for acid. Our pH is 5.36. We have come up a bit since the beginning but it's still reasonable. All right. Now, there is a little bit shorter math equation. It's simply this equation rearranged that you can use whenever you are in the buffer zone. And I don't want to teach you shortcuts until you know and understand what you're doing. So we'll do that in a little bit. Okay. Now, 20 mLs. Oh, man. This is the toughest point. All right. We have to do our dilution. I'm assuming that you can do a dilution. We've done a couple. I'm just going to write our answers down. Our new molarity of our base is 0.0667. And our new molarity of our acid is also 0. It's the equivalence point. They better be equal. That's what the definition of equivalence point is. So 0.0667, 0.0667. For both of those, both of these are going to go to 0, and this is plus 0.0667. All right, start, shift, lost it all, gained it all. All right, now, you can't just follow blindly the math. If you're working on a problem in the classroom and all you're doing is plugging your numbers into whatever your neighbor's doing, you're not going to get it. You have to think about what we have. So remember, this was our acid, this was our base, this is our conjugate base. The only thing we have in the solution is a conjugate base. That's why the equivalence point is basic. Not because stronger one wins, that's just a trick. Our equivalence point is basic because we have a weak base present. It's the only thing present other than water, and we're pretty much ignoring contributions from water, by the way. That's the only thing present. That's why it's basic. You have to be able to justify that. You should be able to think about that and understand that. So let's go. And we're going to do a weak base problem. And I want to try to finish this video, this titration in this video. So this is 0.667. Liquids don't show up, so I'm not too worried about that. 0 and 0. You have to include the water in the reaction because the base has to have something from which to yank that H+. We can just throw an H+ off, and I'll talk about that in class, about the differences in writing these. But when you have a weak base, you have to include the water as a reactant. Now, since this is a base, I'm going to put minus B, plus B, plus B. 0.0667 minus B, B, and B. Now, since this is a weak base, I'm going to set up a KB. And so that's going to be C2H5COOH. If you wanted to define symbols at the beginning of this question, if you defined this at the beginning and said, I'm going to call this HA, that would be fine, but you better define it at the beginning. All right? Over my base. Now, some of you are seeing a problem already in that we didn't give you a KB value. Okay? Well, if you know Ka, you can always get Kb because Kb is simply Kw divided by Ka. Okay, now at 25 degrees, and that's the only one you have to know for this, Kw is 1 times 10 to the minus 14th over, now my Ka, 1.3 times 10 to the minus 5th. Okay? So if we plug that in, we'd get 7.69 times 10 to the minus 10th is equal to B squared over, I'm going to neglect that because this number is greater than 100 times K, and it would be 0.0667. Now, that's the trickiest part of this, is realizing that you're dealing with a KB and that you have to calculate KB. The actual equilibrium calculation's not much different. But here's the key. This is why I use B. As a reminder that when I have B, you have the OH minus concentration. You don't have the H plus. I can't tell you how many times I would have students take minus the log of this number and call it the pH. It's not. It's the POH. So this is the take home here. Whoa, terrible star. If you solve for B, it is 2 steps to pH. That's the only reason, and I'm telling you, since I started switching to A's and B's, I might have 1 or 2 people skip this last step here. So first I have to go to POH. If I took minus the log of that number, I have POH. That's my first step. But remember, we're at a basic equivalence point. That's not logic to call that the pH anyway. pH is 14 minus that, which is 8.86, right? Those two together, if you add those up, remember, equal 14, okay? So POH plus pH equals 14. Hopefully I didn't do that too fast for you. Now, the next one, we're going to have to wait for. This video is 16 minutes, so I will finish that up in our next video. So until then, this is loving you through your journey of learning chemistry.